triple minus 6 minus by 7.7441 times 10 to the power 9 y squared. Okay, so there's a shear stress distribution of the top web. Now we're going to find the shear stress distribution, okay, of the bottom web, right? So like the example that we did earlier, right? Whether you calculate the stresses at the centroid from the top or from the bottom, your QZ has to be the what? The same, because V and I and T are the same whether you take from the top of the web or the bottom of the web, right? Remember I told you guys that, right? Remember when we were doing this example, right? Whether we analyze from the top or from the bottom, the results will be the what? The same. Yes or no? I'm going to do the same down here. Okay, we'll look at the stress distribution from the bottom. Okay, so we will look at from the bottom. So this equation has to be the same. Okay, this equation has to be the same whether you take from top or from, and this is what this is a checking method. Okay, I'll tell you, this is a checking method whether your analysis is right or wrong. If you take it from the top or from the bottom, the answer has to be what? The same. Okay, so now we are going to concentrate on the bottom part. Okay, we're not going to look at the top. All right. So we are going to concentrate on the bottom. So now our y is this way now, right? And then this is our position with stop on the y variable, right? So this is the area of interest, right? Right. So we're going to find the shear stress distribution of the bottom web. Okay, of the bottom web. So when we do this, right, again, we just need to find QZ, right? Or the, let's talk about the limits. So the limits go from 0, y, and they go up to 0.065 meters, right? Why is that? Because if this is 100, right, the distance from here to here is equal to 65 millimeters, okay? So when that's the case, right, we know that our thickness is equal to twice left and right multiplied by 0.02 is equal to 0.04. But let's find our QZ first, okay? So width, depth multiplied by y bar, okay? So the width, so the area, so twice, right, left and right, the width is 0.02, right? And then this is equal to 0.065 minus y multiplied by 0.065 plus y, then the whole thing multiplied by half. Okay, so this will be equal to 0.02 multiplied by 0.065 squared minus by y squared. So this will be equal to 0.065 squared times by 0.02, so it's equal to 84.5 times 10 to the power minus 6 minus by 0.02 y squared. This number looks familiar to you all, right? So if you look at here, right, where I'm highlight, we just calculate this, And the formula, how we get that is different, right? And over here, right, is 80 times 10 to the power 6 plus its different formula, but the final answer is the what? It's the same, right? So whether you take from the top or from the bottom to find the shearing stress as a centroid, it has to be the same, okay? So if you were to say what is the Qmax, so I just copy and paste the same equation. Okay, and there you go. This is for the bottom. That's for the Qmax also, right? So this is the shear stress distribution of the bottom web, right? And at the top web is the same. Okay. The only thing that's different is the flange. Okay, the flange equation is not the same at all. If you look at the flange equation, right, this is the equation distribution of the flange. Okay. Now let's briefly sketch this out. How does it actually look like? So I'm going to do a sketch. Okay, I'm going to label them also. Okay, so we're going to have our. I'm going to like copy this diagram over here. Okay, so we have a bit of reference where we are looking at. One. I like to make this bigger a bit. Okay. So this is the position of our centroid. Yeah, I'm just eyeballing this. Right. Okay. So this is our centroid position. Right. So this is our shear stress. Then we have our axis over here. Right. So this is our y. So over here, this is our in terms of millimeters, this is 35, and at our bottom over here, this is our 65 millimeters. Okay, so it's minus here. So this is 0. So our distribution look like this. Okay, it will come to here, right, and then it will stop, and it will comply to this equation. So this will be equal to 9.483 times 10 to the power 6. 9.483 times 10 to the power 6, and then minus 7.741. 7.741 times 10 to the power minus 9 y squared. Okay. And then we have a step function because the thickness changes, right? The thickness changes, right? Because it's the web section now. So the thickness changes, right? And then we have a curve, right, doing this now. Right? So this equation over here, because either from the top, right, or from the bottom, the web section, the equation is the same, right? So this is 32.707, right? 32.707 times 10 to the power 6 minus by 7.741 times 10 to the power 9 y squared, right? And this point over here, that is our tau max, and our tau max is equal to 32.707 times 10 to the power 6 Pascal. Okay, because if this y is equal to 0, we are left with 37.706. So how do we know that this equation is correct, right? So if we substitute y is equal to 65, right? Tau for the web should be equal to 0, right? So tau is equal to 32.707 times 10 to the power 6 minus by 7.741 times 10 to the power 9 multiplied by 0.065 squared. Okay, sorry. So this is y equal to 0.065 meters. Okay, so when we do that, 0.065 squared times by 7.741 power 9, then 32.707 power 6 minus by this is equal to 1275. So this is approximately equal to 0. Why? Because if you take 1275 divide by 32.707 times 10 to the power 6 multiply by 100%, right? So 1275 divided by 32.707 power 6 times by 100%. So this is equal to the 1275 is very insignificant because it's equal to 3.898 times 10 to the power minus 3% of the maximum value. So it's approximately equal to 0. Okay. So again, this is to show, again, it's quite similar to the sandwich material. Okay, sandwich material is a different ball game in terms of how to find the first moment of area. But I'm trying to show you this, okay? The equation, whether you take from the top or from the bottom, for the web, if the thickness is constant, okay, it will be the same. Okay, I hope you all will use this as a check, okay, a check regarding your equations, okay? Right, so the next section that I'm going to teach, anyone, any questions so far? Anyone? Anyone? Okay, I don't hear anything at all. So the next section we're going to do is we're going to look at long tail. So if we look at our plan for tonight, we have done this one. Okay, so we are going to look at the longitudinal shear of a beam section. And as I said, this topic is it's not difficult. It looks confusing initially because you're new to it. Why? Because this is the first time you're going to do what? Failure analysis. Okay, so this is the first time you're going to look into failure analysis. Okay, so we're going to look at into longitudinal shear. Okay, on a beam section. So we carry out longitudinal shear is to analyze, okay, to analyze right, to analyze the strength of the joint the joints okay, in shear loading configuration. Okay, I'm going to highlight down here the joints. Okay, so the joints right, the joints can either be glued It can either be glued, bolted, nailed,